So we talked about Newton's first law the other day. Newton's first law governs when there is no unbalanced force, or are no unbalanced forces, plural. Okay. If there's no unbalanced forces, then the object will either remain stationary or continue traveling at a constant velocity, which also implies a straight line because to turn still requires a force. Hence, that is an acceleration. Newton's second law deals with all the situations that do have at least one, if not many, unbalanced forces. If there's an unbalanced force, then the object will do what? Not just move. Because an object with no unbalanced forces can move. It'll accelerate. Right? That's the key here. Okay? And so Newton's second law governs a lot more of the real world situations that we might deal with. Okay? We were talking about how a curling rock or a hockey puck or something like that, could travel forever. Okay? But in reality, they don't. Because of what? What is there always between any surfaces? Friction. Friction. Okay? So Newton's second law governs both the accelerating part of this, where I push the chair, okay, and I'm exerting an unbalanced force on the chair to increase its velocity, but it also governs, that's going to hit something. Oh, that was perfect. Okay? It also governs the slowing down part. Okay? Friction becomes the unbalanced force, because once this leaves my hand, once this leaves my hand, the only unbalanced force acting on it is friction. Okay? Gravity and the force of the floor are balanced, okay? Which is why the chair doesn't fly off the ground or fall through it. Okay? It just slowly comes to a stop as friction accelerates it to a stop. Okay? While I'm pushing it, okay, I'm pushing harder than friction. Friction's still there, but I'm pushing harder than that, so the unbalanced force causes the velocity of the chair to increase. Okay, so Newton's second law deals with all of the situations where there's an unbalanced force. Now, it's going to take us like over a week to get through all of those types of situations, and that won't even cover them all. Okay, that just kind of gets you enough exposure to it that you can figure out other situations. Okay, we'll start out really simple, like there's one force, and it's the only force, and it's unbalanced, and we can calculate the acceleration. And then we'll get into, there's several forces. There's 4 forces. There's a bunch of vectored forces, and they make the object accelerate along a different vector. All of these things are going to be what we're looking at. Okay? So, understand the relationship between force, mass, and acceleration. Understand how force and mass influence change in velocity or acceleration. And solve problems related to Newton's second law. So this is Newton's second law, but it should truly be written this way. Not just F equals m times a, but F net equals mass times acceleration. And that should even say the net acceleration. Right? We don't ever write the net on the acceleration, but we often write F net equals m times a. Right? Now, net is just like your paycheck. Okay? If you have a job, you've experienced this pain. Okay? You get your paycheck and it says gross pay. And this is a nice number. And then there's all the extortion, right? There's taxes and CPP and EI and union dues and okay? And then there's this depressingly small number labeled net pay. Okay? Well, net is the sum of all the positives and all the negatives. Okay? Or in the case of forces, it's the vector sum of all the forces. Some positive, some negative, some off at an angle or whatever. Okay? But they all add up to this net force, which is what causes the acceleration. So if my net force ends up being 30 degrees south of east, which way is my object going to accelerate? Exactly, 30 degrees south of east. The net forces vector is always the accelerations vector as well, because the net force is what's causing the acceleration to happen. So they have to go along the same vector. Anyone follow me on that? Okay. So, like we said, Newton's second law deals with what happens when there is a net force acting on an object. Again, okay, we can think about the hockey puck here, and I'll show you a video of what that kind of looks like in just a second. Okay, when the player strikes the puck, okay, he causes the velocity of the puck to change. The cause of that acceleration is the force applied by the stick. Now, that acceleration is only going to occur as long as as long as the velocity increases. What's causing the velocity to increase? Contact with the stick. Okay? That puck is only going to accelerate as long as that force is applied to it. Okay? This is actually, like, this and work energy theorem are the science of sport when it comes right down to it. Okay? It's the science of anything that uses a stick, anything that uses a racket, okay? Anything that is going to exert a force through a distance to cause a change in energy, or a force acting on a mass to cause an acceleration. Okay? The greater the period of time, or the greater the distance over which you can exert your force, the greater you can change the velocity. Okay? And so that's kind of the science behind, let's say, the design of the modern hockey stick. Okay? The modern hockey stick is composite material. It's graphite, it's carbon fiber, it's glue, it's basically not at all what it was 25 years ago when they were a chunk of tree. Okay, like hockey stick when I was a kid was a piece of wood. Right? And wood's a little bit flexible, but it's nothing like the hockey sticks they use today. Okay? When guys take a shot today, they can bend that stick so it's like that on the ice. Okay? They can put an incredible amount of torque into it. And what that does is it increases the distance, because it can snap out the other way as well. It's elastic, right? So it stays in contact with the stick, or with the puck, sorry, for much longer than a wooden stick that doesn't flex very much. Okay? So a wooden stick would only be able to exert a force over that much. So you wouldn't be able to shoot as fast. So the design of the stick increases the ability of you to accelerate the puck. Okay? Same is true of golf. Okay? It's not so much the club, although we also cause the clubs to flex, but the design of the ball keeps it on the face of the club longer. Okay? Back in the day, hitting a golf ball was no different feel-wise than hitting a rock. Okay? It was hard, and when you hit it, it was like a perfectly elastic collision, just bounced right off the face of the club. But now the ball will actually like smoosh into the face of the club, and stay on the club a little bit longer, store a little elastic potential energy, and bounce off. Okay? So again, it's designs like that. Baseball is really about the only sport that hasn't embraced that. Okay? You're still throwing a piece of horsehide at a guy with a piece of tree. Okay? Now, granted, baseball has embraced other types of science. All right, so as long as the force acts, the velocity increases, okay? The greater the force, the greater the acceleration. So if I exert 10 newtons of force, I'll accelerate a mass of 5 kilograms a certain amount. If I exert 20 newtons of force, I'll accelerate that same 5 kilograms twice as much. It's twice as much force, twice as much acceleration, okay? And then if I double the mass, the acceleration will be cut in half. Okay, so mass has an inverse relationship, force has a direct relationship. Okay, and this is kind of, did we talk about this, about the sumo wrestlers? I couldn't remember if that was period 2 or period 3. Okay, like you never see a skinny sumo wrestler, right? Because mass is important, right? You can't accelerate that mass very well. Okay, so one of the most important things for Newton's second law is the ability to draw free body diagrams. That's a diagram that shows the mass being acted on and all the forces acting on it, as though they come from the center of the mass. Okay? So this particular free body diagram is showing one force going to the right, one force going to the left. Okay? We don't know how those forces are necessarily happening, and it doesn't really matter. They're present at the same time, this is what is being experienced by the mass. Okay? This could be somebody pushing the mass from behind. It could be somebody pulling the mass from the front. It doesn't matter. It's a force forwards or to the right. Okay? This force could be somebody resisting from the other side, or it could be friction. Okay? It could be any resistive force, anything that's causing that to act backwards. Right? Now, looking at those two arrows, F1 is bigger. So there's a net force to the right, which means this object will accelerate to the right. Okay? There's a net force, so there will be an acceleration to the right. Okay? So when we were saying that net force is the vector sum of all forces, okay, that's what we mean. We would add these two together, one being positive, one being negative, and we would have the vector sum of all forces. So there's actually two ways to calculate net force. M times A and the vector sum of all the forces. And in most questions, you're going to have to do both. Okay? Like, we're not going to spend 2 weeks on Newton's second law if all it is F equals M times A. That would be like spending 2 weeks on V equals D over T. Okay? The formula is not hard to use. What's challenging about Newton's second law is the nature of all the forces. What are they doing? Okay? How is that affecting the movement of the object? Right? Looking at what's going on there. Okay. Questions on that? Sort of making sense? Okay. Now this is the part, like I said, that can get hairy. It can be super simple like this, one's positive, one's negative, or it can be a bunch of angled ones where you're doing vector component addition, or it could be a complex system where there's a pulley and it redirects forces and it does all of that kind of stuff. Okay? Making sense? Okay, so in Newton's second law, the net force is obviously only one of two factors. Mass is the other factor. All right? So in this situation here, in situation 1, we've got this guy with his golf club and golf ball. So if he swings as hard as he can exert this much force. He'll be exerting that force on an incredibly small mass, okay, the golf ball, which will produce a huge acceleration. Now, if, for whatever reason, he decides to wind up and hit this truck, okay, swings as hard as he can, force is the same, but now he's hitting a truck, so the mass is huge and the acceleration is tiny. Now, usually at this point, people like Coderre, the truck isn't going to move. And I agree with you 100%. That doesn't mean the truck didn't accelerate. Okay? When he hits the truck, if I'm standing at the front of the truck with my hand on the truck, will I know when he hits the truck? Yeah. Not only am I going to hear it, but I'll feel the vibration pass through the truck. So even though the truck didn't roll forwards, the particles, the mass of the truck is still going to move. They're going to vibrate. They're going to move randomly, okay? But they're still going to move. That still counts as an acceleration. And he'll put a big dent in the back of the truck. Change in shape, still acceleration. He moved some of the truck, okay? Some of it didn't, okay? But the whole truck still vibrated, okay? So there still counts as an acceleration. If he did this and the truck was on a perfectly frictionless surface, would the truck move? Yes. Okay, the truck would slide, actually, it wouldn't even roll. If the surface was frictionless, it would slide after he hits it. Not very much, okay? And remember that the acceleration would only occur as long as the club is in contact with the truck, okay? So it's a small acceleration over a very small amount of time. You'd barely be able to perceive the movement of the truck. And after, the truck would move at a constant velocity, very small constant velocity, because now all the forces would be balanced again. He's no longer hitting the truck, there's no friction. Okay? The truck would just slowly slide away from him. Kind of like what happens in the parking lot sometimes. Okay? Who's ever had that happen? It happens in the teacher parking lot. I actually parked my truck up on the bank, And then I came out at lunch for supervision, and my truck was out in the like driving area because there was so much ice there that I had parked it, gotten out, gone into the school, and while I was out there, it had actually slid. And maybe the wind had rocked it enough just to get it going, and then it slid on the nearly frictionless ice right out into the driving area, okay, until it got some bare asphalt and the tires ripped and stopped it again.
Another example would be like an air hockey table.
Absolutely, air hockey is very, yeah, it's very low friction because you've got air blowing up on the bottom of the pucks, and so they don't push down on the table as much. The table doesn't push back, so there's less friction. Okay, is that idea all right? So that's again illustrating that effective mass on acceleration. Bigger the mass, smaller the acceleration. All right, so when a net force acts on an object of a certain mass, the acceleration that results is directly proportional to the force and inversely proportional to the mass. So as mass gets bigger, acceleration is smaller. As force gets bigger, acceleration gets bigger. Okay? Now, the units for force are newtons, but that's not the fundamental unit. We just say newtons because the fundamental units are more complex and it's easier to say newtons, plus we honor the guy that came up with all this. Okay, so when I multiply mass, which would be in kilograms, by acceleration, meters per second squared, I get the units for newtons. A newton is a kilogram meter per second squared. Okay, you never need to write it that way. You can just write N for newtons. Okay. But just know that the units for newtons are kilogram meters per second squared.
So do you always have to convert your mass to kilograms?
Yes.
For it to be a newton?
Your mass, for all physics, mass is in kilograms. Okay? In physics, we deal with everything from an electron to a supermassive black hole. Okay? So we use kilograms. We go big. Okay? Chemistry always deals with atoms, so they use grams. Okay? But in physics, it's always going to be kilograms. So if it's given to you in grams, convert to kilograms. I can't think of too many situations where it'll give you grams. It's going to mostly be kilograms. All right. So free body diagrams. Okay? This is not how to draw them. That is how to draw them. Okay, so we draw the forces as though they come out of the center of mass. Sometimes we call that center of gravity, okay, but technically it's not where gravity comes from. It's where the center of the mass is. Okay, so we have the reactive force or normal force, okay, and we have the force of gravity. So this would be any object sitting on a flat surface. Gravity pulls it into the surface reacts and pushes back with an equal and opposite force, and thus the net force on this object would be 0. Okay, the force down and the force up are equal. Object isn't going anywhere. Okay, so important to be able to draw free body diagrams. That's going to be your givens for any problem in this unit. Okay, being able to draw that mass, and everything is just a box. Okay, doesn't matter what it is, whether it's a bicycle or a wagon or a box or anything. Okay, it's a box when you draw it. That way people like me who can't draw are okay. All right, let's try this one as our first example here. Okay, so I want you to write this one down. Okay, anybody ever have to do this? Okay, push a stall car. How many of you have a car that is a standard transmission? Okay, so yeah, it's becoming less and less common. Basically, everything has an automatic transmission. Back in the day, this is how you could start a car with a dead battery. If it has a manual transmission, you can start it on compression, which means you don't need the battery to turn the engine over. You just push the car, and someone inside leaves it in neutral, puts in the clutch, puts the transmission in second. And then when you get it going, they just pop the clutch. And the force of the car moving will get the pistons moving up and down, and the engine will ignite. okay, because it still compresses the fuel, okay, and gets the engine actually running without having to use battery power to start it. You can only do that with a standard transmission. You can do it with an automatic, but you have to get it going like 30 kilometers an hour. So good luck with that. And I mean, you could push it down a hill, I guess. But then there's also the problem of taking an automatic transmission and jamming it into gear while the car is in motion. That's generally very unpleasant. Yeah, the grinding sounds that happen are very bad. It works very well with the standard because you can open the clutch, okay, and kind of engage it slowly. But that's how we used to do it. Okay? So in this situation, we have an 1,850 kilogram mass. So when I'm drawing my free body diagram, the car becomes a box. And I draw the mass in the middle of the box, 1,850 kilograms. One person applies a force of 275 newtons forwards. The other person, 395 newtons. So one of them hits the gym and the other doesn't. Okay? And friction is acting on the car, but it is in the opposite direction. Right, now, you'll see I still reflect scale in my free body diagram because I want to reflect scale in my vector diagram as well. Although, do I need to draw a vector diagram for these forces? They're collinear, right? I wouldn't bother drawing a vector diagram of these. Okay? I know that this one's negative and these two are positive. Right? So now I've got my free body diagram. I want to find the acceleration of the car. Okay? Well, F net equals m times a, and it equals the vector sum of all forces. So that's going to mean 295 plus 395 plus negative 560. That would be my vector sum. Agreed? Okay. So when I do that, okay, so 275 plus 395 minus 560 gives me a net force of 110 newtons. Okay, I want to calculate acceleration. What do I do with m? Divide it over to the other side. Okay, so divide that by 1,850 kilograms, and I'll have my acceleration. It's going to be pretty small. All right, 0.059 meters per second squared. Okay, so that means like 6 centimeters per second squared. So every second, the car will be going 6 centimeters per second faster than the second before. So it'll take a little while to get this thing doing anything. But as long as they keep pushing, that acceleration will continue. And eventually it'll get moving fast enough that they have to run after it. After they pushed it for an hour. But yeah, eventually. All right, everybody understand how that one worked? Okay, so that's a very basic example of a Newton's second law question. I had to do vector sum of all forces, and I had to do m times a. And in basically every question except the simplest ones, you would have to do both. Obviously, it becomes more complex when you're having to identify the forces. You're having to figure out maybe they're vectored, so you're having to bring vector diagrams into the whole situation and all of that. Okay? But that's essentially what it comes down to. Okay? Every Newton's second law problem boils down to these two things: the vector sum of all forces and m times a. Okay? So a question might say, there's an object with this mass and this acceleration, and here's a couple of forces that are acting on it. Calculate the missing force. Okay, well then I would have like m and a, I would have 295, 395, and x. And I'd have to solve for the missing force. Right? So sometimes it's going to ask you to calculate one of the forces. Sometimes it's going to say, here are all the forces, calculate the acceleration. All right. Questions there? All right, so that's what we just did. Okay, that's all the math that we just did. Okay, I want you guys to try this one. It's got vectors in it, but that's no problem for you because you guys are good at vectors. Okay, so you got that box there. It's 15 kilograms. It's on a flat, friction-free horizontal surface, so like an air hockey table. Okay? And you're looking at it from above. Okay? The two forces are 35 newtons, 60 degrees above the x-axis, and 10 newtons along the x-axis. Find the acceleration of the block. Okay? So, did they already kind of do the free body diagram for you? Okay. So, what I would do is ignore this diagram because it's really misleading. Okay? But here's your free body diagram. This is our 35 Newton force, and this is our 10 Newton force, and then this is our 15 kilogram block. Okay? So net force is the vector sum of all forces, and we're trying to find the acceleration. I'll give you a couple minutes on that, and we'll go through it together. All right, so we've got the free body diagram, but if we're going to get the net force, which is the vector sum of all the forces, what kind of diagram do I need to draw next? A vector diagram, yeah. These are vector quantities. I have to add them like I would add any other vectors. Okay. Now, if I use a kind of a little bit of visualization here, if I have a force acting this way and a force acting this way, which way is the box going to move? Like diagonally up that way, right? But not quite as steep as that 35 Newton force. Okay, tempered a little bit by the 10 Newton force. Well, that's exactly what I would get if I drew the vector diagram. So here's the x-axis, okay? There's my 60 degrees, 35 newtons, okay? So it's got a y and an x component, and then I've got my 10 Newton force on the head of that, going straight horizontal, which means my object is going to move that direction. Well, that green line is my net force. It's the vector sum of the two forces that are involved here, right? And so it would be no different than a vector addition question in Unit 1. In fact, one of the questions on your vector assignment was two dogs, I think, fighting over a bone, okay? And they were pulling on it in different directions. That's this. Okay? It's exactly the same as this. I'm going to find the net force by finding the resultant here. Okay? So this would be y, and this would be x. Okay, so when I do this, I've got to find my x and y components for the 35 Newton one. So I'm going to go sine of 60 times 35. So that'll be 30.31. Okay, and x is going to be the cos of 60 times 35, which will be 17.5 newtons. Okay, so this is up and this is over, okay? And then our 10 Newton force, okay, is just going to add to that. So green y is going to be 30.31 because there's no other y components, okay? And green x is going to be 27.5 newtons, okay, along the x-axis in the positive direction. And then I can find my result, okay? My resultant will be my net force. So okay, so my net force will be 40.93 newtons. I need my vector because my acceleration, which is what they want me to calculate, has the same vector as the net force. Okay, so that'll be inverse tan of 30 over 27. Okay, so 47.78 degrees. And that'll be above the x-axis, right? So now they want me to calculate the acceleration. What do I do with this number? Okay, so what we just did here is we said, F net can be calculated in two ways. The vector sum of all forces, which is what we just spent all that time doing. And that equals m times a. How do I find a? Divide both sides by mass. Okay, I just calculated this. I divide by mass, I've got acceleration, and they told me the mass was 15 kilograms. Okay, so I take that net force that I just calculated, okay, the 40.93, divided by 15. All right, so my acceleration will be 2.7 meters per second squared at 48 degrees above the x-axis. So not a lot different than what we did in terms of the vector part of it. Okay, we just add on this m times a part at the end. All right, we'll call it there. So like I say, Newton's second law we're spending a lot of time on because there's a lot of things governed by it.
Active on